Hello everyone, welcome to today's lesson. This lesson is on electrochemical cells, some of the most widely used technologies in the world. These methods are used to generate electricity for portable devices. We're going to talk about how they work today. So, for any spontaneous electrochemical reaction, we know that the delta G must be less than 0. The reaction is irreversible. Now, suppose we took a piece of copper metal and we dropped it in a test tube containing silver nitrate. Silver metal will form immediately, and the copper reacts to form cupric ions. So we're going to take a look at this in detail. Here's the overall reaction. You can see from oxidation states, we can see copper goes from a 0 oxidation state to a 2+ oxidation state over here, and silver goes from a 1+ oxidation state to a 0 here. So if we use, again, oxidation numbers like we learned in the last lesson, it's easy to identify what is oxidized and what is reduced. Copper going from a 0 to a 2+ state tells you it's being oxidized. Silver going from a 1+ to a 0 state tells you it's being reduced. So here we have a video here. I'm going to speed it up to show you the reaction. Just go to the start. Here we have the copper metal sitting in a solution of silver nitrate. And over time, what happens is the silver starts accumulating on the surface of the copper, and another subtle change starts to happen. You can actually see some activity here because there is heat generated. Those are little particles of silver that are not quite stuck to the copper. They will eventually stick back to the copper. But over time, I'm just going to speed the video up. You can see what's happening. The blue color is coming from the oxidized copper. It is forming cupric ions in solution, and that gives you that beautiful bluish color. So one of my favorite reactions to carry out, it produces that gorgeous color. So we can take it to completion here, and we don't need to see that anymore. So we can keep going. So again, there's the overall equation for the reaction. So let's talk in detail about what's happening here. Now, there's no work that's going on because there's no changes in volume. This is also being carried out at constant pressure. So we know changes in internal energy must be coming from heat alone. So the change in internal energy is happening spontaneously here as the copper is introduced into the silver nitrate. But it's a very inefficient way of using energy. There's a much better way of harnessing that energy, and that is going to be done by isolating the copper from the silver nitrate. So the reaction doesn't happen in one container. It actually happens in two. And we can force the electrons that are being shed when the copper metal is being oxidized to flow through an external circuit and do work for us. So let's take a look at a picture of a cell that accomplishes just that. So we call these types of cells galvanic cells in honor of a man named Galvani, who was an Italian scientist, actually a doctor who worked in the 1700s in Bologna, Italy, and he, by urban legend, is reported to have been working on frogs with static electricity, and he was rubbing the leg of a frog that was dissected to create static electricity, and apparently accidentally touched a nerve with a metal scalpel or probe in the frog leg, and the frog's leg contracted, and he discovered what he called later animal electricity, and had a theory for it. There was a fluid flowing in the frog leg to actually cause the electricity to flow in the nerve, which of course contracted the muscle. So now copper, in this case, copper is being oxidized. The electrons are flowing through an external circuit. So let's take a look at all the reactions. Copper metal is changing into copper ions, releases 2 electrons. The cupric ions are being generated here, and it's causing the solution to turn blue. So as the electrons flow through the circuit, they arrive over at the silver electrode, and at the surface of the silver electrode, those electrons are being used up by the silver ions. So now let's look at detail here. Here's a picture of copper atoms. The copper atoms are losing electrons. The electrons are, of course, because they're negative, they repel, they flow through the conducting wire. The ions are being generated in solution, so the copper atoms are changing in the copper ions. Now at the other electrode, the silver electrode, let's investigate what's happening. So the silver ions in the solution of silver nitrate are now joining with the electrons that have been released from the copper atoms, and they're forming silver metal. So the silver electrode is going to increase in mass over time, and the copper electrode is going to decrease in mass over time because of this reaction that's happening. Now, a little bit of terminology. We always use the term cathode in a galvanic cell to represent the where the reduction reaction happens. And the formation of positive ions is occurring at the anode where oxidation is happening. Now, a little bit of explanation for why a salt bridge is required. Because if you ever set up one of these cells with a salt bridge, and I did many times with my students in high school, if you pull this salt bridge out, the cell stops. Now, the reason for that, well, you can see that these copper atoms changing the copper ions are going to cause a buildup of positive charge. Well, the buildup of positive charge is going to have a repulsive effect on the further production of positive ions. So without the salt bridge, that reaction will not continue. But with the salt bridge, what happens is negative ions will migrate from the salt bridge into the solution to neutralize the positive charge and keep this solution neutral. So more copper atoms can be oxidized. So for every copper atom that's oxidized to cupric ions, you're going to need 2 nitrate ions migrating into the solution. So the nitrate actually, if you use solutions of nitrate, which they have in this cell, the nitrate will migrate all the way from one side all the way to the other. So we'll get a continuous flow of nitrate ions in this direction. So now, again, let's look at what's happening at the silver electrode. The silver electrode is gaining electrons. So the silver ions are joining with the electrons released from the copper and forming the silver metal here on the surface of that electrode. So now the opposite thing happens here. With silver ions being consumed, the silver ions are leaving the solution. They have to be replaced. So the positive ions in the salt bridge here, potassium nitrate, the positive ions will migrate in, and of course the copper ions will migrate in to take the place of the potassium. So what you're going to get is a constant flow of the copper ions in this direction. Now, because the positive ions are flowing towards the cathode, they're called cations. So another little bit of a terminology here. So the positive ions in the right-hand beaker, so they flow like I was showing here. The positive ions are flowing from the left side of the beaker to the right side of the beaker. And the negative ions are flowing towards the anode. They're called the anions. So the negative ions are flowing in this direction. Now, the way I remember it, the N in the word anion is associated with negative, and that T in positive looks like a positive sign. That's how I remember that cations are positive. You can see a T here in the word cation. Again, positive, like a positive sign. Anion, the N, negative. So I hope that helps you. So further terminology, oxidizing agents, the substance that causes the oxidation of the other substance. In this case is the silver ion. It's gaining electrons. So the reducing agent is the copper metal. Because it's being oxidized, it's actually causing the other substance to be reduced. That's why we call it the reducing agent. So the anode, again, oxidation happens at the anode, and reduction happens at the cathode. Notice that we balanced the equation here with silver. There are 2 electrons that are being released for every copper atom that is being oxidized. So the silver actually has to be multiplied by 2. So we're going to multiply this whole equation by 2 so we can balance the electrons and add them up. When we add them up, we can get the overall reaction. So this is very important terminology for problems. We always write the oxidation on the left side, the reduction on the right side. You can see from this script, copper metal is being oxidized to copper ions. It's in a solution of 1 mole per liter electrolyte. In this case, the electrolyte's copper nitrate. The 2 lines represent the salt bridge, which potassium nitrate serves admirably in that role. You want to use an electrolyte that does not participate in the chemical reactions at the electrodes. Potassium nitrate is one such electrolyte. And on the other side, we have silver ions changing into solid silver. So the anode is always on the left of the double line, and the cathode is always on the right of the double line. And there's an interface, again, between the copper and the copper ions, similarly between the silver ions and the silver, and the double line is the salt bridge. So when we add those 2 together, we get the overall reaction. Copper is oxidized, silver ions are being reduced. Now, how do we design a cell to separate the overall reaction in the 2 half reactions? So we simply put them in 2 separate beakers and allow the electricity to flow through the external circuit. And the potential energy changes would be converted into heat if they're in the same beaker. You're still going to get a bit of heat here, but you're going to also, because the wire is going to heat up to some degree, but you will now be able to harness the flow of electrons from one side of this cell to the other. So again, the purpose of the salt bridge is to maintain electrical neutrality. As we mentioned earlier, as the copper ions are being created, we need to neutralize that plus charge, or else it will repel further oxidation. To do that, again, we're going to need negative ions migrating in to neutralize the cupric ions. And on the other side, when we use up the silver ions, we're going to need to replace them with other positive ions. So the positive ions, if you may, are going to migrate. We're eventually going to find copper ions in here as well. So this solution will, if you run it long enough, you'll start getting positive charges happening over here. So in a perfect world, we could stop the copper from flowing in here and just keep and put enough electrolyte in here as the cell works to just keep replacing it with the potassium ions. So the charges will remain neutral in the solutions here, but again, the silver will build up on the silver electrode and the copper will decrease in mass as this reaction proceeds. Now, in summary, the electrons move from one side to the other, transfer of electrons brought about by these 2 redox reactions, and the solutions are moving in the opposite direction. So the ions. So the electrons move this way, and we get ion movement happening in the other direction as well. So you get both positive ions migrating left to right, and you get negative ions migrating right to left. That kind of completes the electrical circuit. Now, electrochemical cells composed in this way that generate external electricity for use are named after Galvani. Again, a scientist, Italian medical physician who experimented with frog legs and discovered animal electricity. Now, we can actually force chemical reactions using electricity. We can force them in the opposite direction, and those types of cells are called electrolytic cells. When you have rechargeable batteries, you're actually performing the reaction in reverse. This is really a form of an electrolytic reaction. So here's another cell we're going to talk about. In this one here, we're going to talk about a copper zinc cell, and we're going to look at it in detail.
operates. Here at the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution. Loses 2 electrons and becomes a zinc ion, which diffuses into the solution. The electrons given up enter the bar and join the flow of electrons up toward the external circuit. They travel through the wire and flow into the cathode, the site of reduction. When a copper 2 ion in the cathode solution makes contact with the copper electrode, it gains 2 electrons and is reduced to a copper atom, which deposits on the bar. Therefore, as the cell runs, the zinc anode becomes lighter and the copper cathode heavier. Now let's close in to see the role of the salt bridge. The non-reactive sodium and nitrate ions of the salt bridge prevent the buildup of charge that would occur as zinc ions enter the anode solution and copper 2 ions leave the cathode solution. Such a charge buildup would halt cell operation. In the anode compartment, nitrate ions leave the salt bridge to balance the gain of positive charge as zinc ions enter the solution. Some zinc ions also enter the salt bridge. In the cathode compartment, sodium ions leave the salt bridge and nitrate ions enter it to balance the loss of positive charge as copper 2 ions leave the solution and are reduced at the cathode.
All right, so now continuing on here. Okay, so let's talk about what just happened. Let's summarize it. So there's 2 half reactions. What I'd like to do is pause the video for a minute and then draw the cell yourself, identify what's oxidized, what's reduced, the oxidizing agent, the reducing agent, and describe how the electrons flow through the circuit and how the ions flow in the cells. So now that you've paused it, let's take a look. So here is a picture of it. So again, we're showing the oxidized substance on the left. Zinc is being oxidized to zinc ions, and copper ions are being reduced to copper metal. Each electrolyte in here, the zinc nitrate was 1 mole per liter, the copper nitrate was 1 mole per liter, and in this example, we've got a potassium nitrate salt bridge. In the video, I believe they use sodium nitrate, so you can use either, they're both soluble. So the copper nitrate was dissolved in that solution, the zinc nitrate was dissolved in the other solution. The oxidation resulted in a positive 2+ zinc ion. Now, to maintain electrical neutrality, of course, we're going to have the flow of ions, negative ions, to balance out the zinc ions. But as the electrons flow through the circuit, of course, they do work for us, like turn on a light. So the nitrate ions are going to migrate in, and again, we're going to get nitrate moving in this direction, and the zinc ions are flowing this way. As the copper ions are being reduced to copper metal, we need to replace those positive ions to maintain electrical neutrality. So the zinc ions, the potassium ions will migrate, and then the zinc ions will follow. So you'll end up with zinc flowing this way, and nitrate ions flowing this way. And I'm illustrating that here. So again, the oxidation is happening at the anode. The zinc atoms are oxidized. The mass of the zinc will decrease over time as the concentration of zinc will increase. And the region around the zinc ion becomes positive, so negative nitrate ions migrate in to maintain that neutrality. Now on the other side, the reduction side, copper ions are being reduced to copper metal. The region around that solution will become less positive, so that we're going to have positive potassium ions migrating in to take their place from the salt bridge. And zinc, of course, will eventually flow over there as well. So now, some galvanic cells use inert metals like gold or platinum or iridium to act as a surface for redox reactions to take place. So in that case, here's a picture of a standard half cell. of hydrogen with a half cell of copper. We're going to talk about the standard half cell in the next lecture. But for now, I just want to show you the terminology. There's no oxidation happening at the surface of the platinum electrode here. What we're doing is we're bubbling in hydrogen gas at a pressure of 1 atmosphere, and there's a reaction happening at the surface of the platinum electrode in which the hydrogen gas is changing into hydrogen ions. And we can depict that with this descriptor. It shows there's a platinum electrode, and again, oxidation's on the left. So the hydrogen gas is oxidized to hydrogen ions, and the copper ions are being reduced to copper. So the copper metal is going to increase in mass over time. The platinum electrode is not going to participate in the reaction. It's just acting like a surface area. Now, platinum is highly expensive, is very expensive. So they make the platinum electrode really thin. That also serves for increasing surface area. So platinum is one of those metals that you can pound into extremely thin sheets. Gold is the same. Platinum and gold are both very expensive metals. So they use small amounts when they create these cells. So we have 2 half cells together. They create a functioning electrochemical cell, galvanic cell, that is producing electricity. So the electrons will flow from the electrode that is being oxidized to the electrode that's being reduced in this case. So it's like a tug of war, a molecular tug of war. In this case, the copper is winning the tug of war. It's pulling the electrons away from the other side, where the hydrogen gas is being oxidized to hydrogen ions. And of course, we could monitor this, the state of the reaction, the degree to which it is occurred, the reaction rate, if you may, by monitoring the acidity in the solution. So the acidity is going to increase, so the pH of this will go down over time. Similarly, you should get a reduction in the blue color over here. So we could actually measure the concentration of copper in this side using colorimetric determinations. So where you measure the amount of light absorbed in the solution with a spectrophotometer, and over time, as the blue color decreases, then you will note that there's less light energy being absorbed in the spectrophotometer. So now, Michael Faraday, a gentleman who worked in this field and established a mathematical relationship between the electrons that flow in a galvanic cell. So we're going to solve some problems here using some of the concepts that Faraday developed. So we can figure out the charge on a mole of electrons by knowing the charge on a single electron. The charge on a single electron is given as 1.6 times 10 to the minus 19 coulombs for every electron. And if we multiply that number by the number of electrons in a mole, we end up with the charge on a mole of electrons, which this number will be given to you on your formula sheet for calculating these types of problems. So we call that quantity, 96,485 coulombs per mole, we call that a Faraday in honor of Michael Faraday. So now, to show you how a problem is done, here is an example of copper changing into copper ions. So copper is being oxidized, silver is being reduced. So we're going to calculate the mass of the copper that is going to be lost by the copper electrode and the mass of the silver that's gained by the silver electrode if we pass a current of 0.5 amps through the cell for 101 minutes. So remember, charge equals current times time. So to solve this problem, the time is in minutes. We're going to have to convert it into seconds. So to show you how we do that, again, there are the 2 reactions that are happening. First thing we're going to do is figure out the time in seconds. Every minute has 60 seconds, so we end up with 6,060 seconds. Because the current is given in amps, an amp is really a coulomb flowing every second. So since this quantity was amps given in the problem, which is a coulomb per second, we are going to convert our time to seconds. So once we do that, we can figure out the total charge that was transferred in this particular cell during that 101 minutes. So we calculate the charge to be 3,030 coulombs. Now we can convert that into the number of moles of electrons that actually were transferred. We know how many coulombs of charge there are in a mole of electrons. So if we divide the number of coulombs by the number of coulombs in a mole of electrons, we can end up with the number of moles of electrons. And now that we have calculated the number of moles of electrons, we can use the stoichiometry in the balanced half-cell equation here, because we see the relationship between the mass of copper and the mass of electrons. 1 mole of copper is used up for every 2 moles of electrons that are being generated. So, of course, if 2 moles of electrons are produced from 1 mole of copper, the mass of copper will be the moles of electrons multiplied by 1 mole of copper over 2 moles of electrons times the mass of 1 mole of copper, 63.5 grams in a mole of copper. So that gives us the mass of copper created, or used up, I'm sorry, in this case. Copper is being consumed. We can see that from the terminology used to describe the half cell. And now we're going to look at the amount of silver that's produced, again, using the stoichiometry in the balanced half cell equation. So the mass of silver will be the number of moles of electrons in 101 minutes generated by that current of 0.5 amps. So we're going to multiply, in this case, by 2 moles of silver for every 2 moles of electrons. So it's a 1-to-1 reaction ratio. So the molar mass of silver is 107.9 grams for every mole. And when we multiply and cancel out, again, our moles of electrons cancel, our moles of silver cancel, and we're left simply with our answer in grams. So we're going to make, in that time frame, in 101 minutes, operating the cell at 0.5 amps, we are going to make 3.39 grams of silver, and we're going to use up 0.998 grams of copper. So you'll be expected to carry out problems of this type on your next quiz. So to prepare for that, please make sure that you read your textbook and carry out these assigned questions that are in your course pack. So have fun with that. And remember, chemistry is not a spectator sport. You have to do the questions to prepare yourself for the evaluation. And a reminder, this is the last lecture that will be covered on the quiz that will be next Friday, which is Friday, May the 29th at 2 p.m. All right. Have a great day and have a productive work session. Thank you very much. And